the macro basis deployment, we can see some significant energy saving. That's what they are talking about. Right, so let me skip this slide. It's a little bit similar problem. So first research is looking at the kind of a joint BS topology, micro basis station topology, and the BS on-off problem, right? So this is another paper which is looking at the joint of the BS on-off and association. So they are just scaling down the time scale just a little bit, even if they are looking at a similar joint problem. So this is my paper, and again a similar the model and objective. And the system model is that we were looking at the floor level location dependent capacity, where the objective is that so we want to minimize which basis stations should be turned on, and also we have to find the rho, which is the traffic intensity, so that we can minimize this guy. And what is this? This is the sort of the cost of the floor level performance, which is quantified by the delay. So we use the delay as a quality of service, and the eta is a sort of the balancing weight between the energy efficiency and the quality of service, and then these are the energy consumptions. Okay. So that's another problem formulations that we looked at. So but I know that you might not be interested in which detailed problem formulations. This is just one example of how we look at the BS on-off problem and the basis station BS association problem. So again, here, when we look at this problem, then clearly we can see the time scale separation again, right? Because the BS operation will take, typically it will take several hours, but the user association will happen with the order of the minutes. So we can decompose these problems where we first find what basis stations should be turned off depending on the model, whatever model that we use. And then, given the basis basis stations, we look for the optimum rho, which can minimize this sort of user level performance. And then this involves in the user association problem, because if we turn off some basis stations, some users should be determined, okay, which basis station do I have to associate with, right? So it includes the user association problem. Again, I will just scan through, okay, what type of the problems have been looked at by some academic people, right? And this also shows some simulation result where, so here the lambda is sort of the traffic intensity that we have to handle. So depending on the lambda, then we vary the balancing weights between the performance and the energy efficiency, which is denoted by eta. Then we get this kind of curve where the y-axis is the total power consumption and the x-axis is the sort of QoS factor. So we believe that this region is something called the greening zone, where essentially we can see the concave performance and the energy trade-off. So even if we decrease the total power consumption much, but the quality of service does not vary so much. So this is some spot that we have to enjoy. Another problem in the time scale of the millisecond, this research is so the motivation is that, as I mentioned before, cells are becoming smaller and smaller, right? So interference management are becoming more and more important. So, for example, in the 4G LTE or WiMAX system, on the OFDM based system, they are thinking about how can we dynamically control the power, so that sometimes we have to focus on the HE users, sometimes we have to focus on the center users, and so on. So dynamic power control is expected to be deployed, and then when we run the dynamic power control, we should run this thing, or we should formulate the problem given the power budget, okay? But the interesting question is that the Kyoto Protocol, that means that it is expected to enforce the limit of the annual energy consumption per country. I'm not sure that the Kyoto Protocol is enforcing that or not, but we can expect that kind of scenario. So we want to address some interesting question. Is that okay? If some country like Korea, for example, they have some limit of the annual energy consumption. It's actually not annual energy consumption. It's a CO2 emission, amount of the CO2 emission. And then probably the country is worrying about, okay, we have to have some kind of energy budget that we have to run the country, for example, and then there are a lot of industries, in the mobile industries, for example, then please limit the amount of the energy that you are using by some number, okay? It does not have to be concrete, but that can be some number. So in that case, from the perspective of the person who are developing the resource allocation algorithm, especially here in this case, power control, there could be many sharing mechanisms of the given version. All right. So one example is that, okay, suppose that like some mobile network provider in Korea, for example, they have some power budget. Okay. So how can we share this power budget? So one easy of doing that is that, so we can classify this using the power budget based on the spatial sharing as well as the temporal sharing. Meaning that, okay, you guys have to use this power budget over like 1 year. This is the power budget over 1 year. So then one thing that the mobile network provider can do is that, well, they have some degree of the freedoms to use that power budget. So overall, on average, it's okay to use just that amount of the power budget. But from the perspective of the making the box, making the devices, it's very convenient to that, okay, when we make the base station, that we sort of limit the maximum power of the base station. So that does not have a full degree of the freedom, right? So in that case, we classify the sharing mechanisms, power budget sharing mechanisms across the two dimensions, temporal and the spatial, where the spatial means that, okay, we can sort of set the limit of the power budget at the cell level, meaning that base station can use this kind of maximum power, or we can enlarge this degree of the freedom for sharing the power up to the network level. For example, one overall network of the one mobile network provider. So if we can increase the degree of the freedom, and also in the time domain, for example, at every time instant, you have to use this maximum amount of power. No, you can use some more power, but overall, on average, you have to use this limit of the power budget. So that's the kind of degree of the freedoms that we can enjoy for the sharing of the power budget. It's very clear that if we have a full degree of the freedoms from the perspective of the spatial sharing and the time sharing, we will have a more performance increase, right? Because we have a full degree of freedom. So we can use you can use a small power in this cell and we can use a large power in this cell depending on the user's locations and so on. Of course, the system that we have to employ or implement in order to enjoy this spatial level or temporal level full degree of the freedoms of power sharing, then the system becomes much more complex. So that's the trade-off. So we are just interested in what happens if we increase this degree of the freedom of the power sharing. Is there any significant power saving and so on? So that's the question that we wanted to answer. And then we typically we employ the typical ways of looking at the dynamic power control problem. And then I skipped all the slides and then I just show some representative graph where. So we have many sharing mechanisms. And if you look at this red guy, this is what is beta? So beta is the amount of the reduced power budget, meaning that if the beta is 0.5, then from the maximum power budget that we can use, we just use the half of the power budget, right? So that's the greening factor. So if we use the full kind of power budget, but if we employ ST is 0, then we don't have no degree of freedom of the power sharing, meaning the instantaneous power budget and also the cell level power budget. These guys is the maximum kind of max guy, and this is the sort of achievable capacity without power budget sharing. So if you look at this number, and then if you withdraw this line, then we can meet here at this point. What does that mean? Means that if we can apply some level of the greening, like 20%, but we can achieve the same performance. So depending on the power sharing mechanisms that we can have some numbers about how much performance increase we can get. So it looks, this is just an example that it looks very important to dynamically use the given power budget, but the question is how can we implement the base stations as well as other networking equipment so that we can fully enjoy those full power sharing, the power budget to be shared. Okay, so right. Let me conclude my talk. I just talked about some greening policies. So there could be many greening policies, but as an example, according to different time scales, I just show some example researches or case studies of the BS topology, on-off, and power control. So it's always convenient, at least for me, to look at the greening problems with using this some kind of criterion of the different time scales. There are some messages probably that I can think of. I guess there are still many spots for greening, as you can see my talk and also Professor New's talk. And probably there are many open problems. This is one example that I can think of, like how can we cooperate each other among the multiple mobile network providers, and also, all the BS control mechanisms should be coupled with other greening policies, for example, like smart antennas, and also I did not mention that the backhaul greening and so on. So there should be some impact or the interplay between these two guys. And also, I was thinking that, okay, is there any way of letting the users participate in this greening approach? Okay, greening is something that only the network providers or the equipment makers should be worried about. So, is there any mechanism of doing? I don't have any clear idea, but I was just thinking about these issues and so on. So, I hope that there are many blue ocean spots for the greening research. Okay, that's my